Welcome to Piecewise Functions, a pre-calc and calculus perspective. In this video, we will talk about what a piecewise function is and kind of build back from the beginning. So we'll evaluate a piecewise function, we will learn how to graph it on Desmos, and then we'll explore limits, so look at them from a calculus perspective. So let's head back to the beginning. Here's a piecewise function. It is still in the form of a function, but it has different pieces. And we would call this function's breaking point, or the x value at which it changes, at -1. You can see that when x is less than or equal to -1, we have a linear function, and when x is greater than -1, we have a quadratic function. So we can call this like the top piece or function or equation, and we'll call this one like the bottom piece or function or equation. And we'll say that like the breaking or change point is at -1 because that's where we switch from linear to quadratic. All right, so let's first just do basic evaluating the function at 3 different x values. This means the exact same thing as it means if this were a regular function. We're going to plug 2 into f, and what we need to do is decide which piece to use. So 2 is greater than -1, so we're going to plug in 2 to this bottom part right here. So when we evaluate at 2, we'll have 2 squared plus 2, which is 4 plus 2, so that value is 6. That means that when we input 2, our output's 6, so we'll later see that the coordinate point 2, 6 is on the quadratic piece. All right, let's plug in -1. This one is at the change point, so we have to decide which part it belongs to. Since this is x is less than or equal to -1, we'll plug it into this top piece right here. So when we plug in -1, we'll have 5 minus -1, which also happens to be 6. So we'll have the coordinate point -1, 6. And lastly, let's plug in -3. That belongs here as well, since -3 is less than or equal to -1. So we'll have 5 minus -3, which is 8. So that's just basic evaluating a piecewise function. And now let's learn how to graph this on Desmos. All right, we can see that we have 5 minus x already plugged in, and that gives us this line everywhere, but we only want the line when x is less than or equal to -1. So what we need to do is get brackets. The way that we do that is we're going to hit this ABC button, and then we're going to select the brackets, and then inside those brackets we'll go back to the 1, 2, 3, and then we'll select, make sure we're on the inside, we'll select x is less than or equal to -1. And so that will only graph the piece of the function that we want. So we can see that our linear function ends when x is equal to -1, and it's only to the left of it. Now the only thing Desmos is not going to do is show a distinct closed or open hole at the end. This should be like a closed dot here, technically, because it can equal when x is -1. And we saw before that when we evaluated at -1, our output was 6, so this is the coordinate point -1, 6. All right, now we need to graph this second part of our piecewise function, the quadratic piece. So I'm going to click this plus key here to add another expression. And if you want to put f of x equals, you can. I just typed the function. So we'll hit the x key, and then hit the little a squared button to get x squared. Then we'll do plus 2. And again, we need to get those brackets. So again, we'll hit the ABC button, hit the brackets down here at the bottom, go back and do x just is greater than, this time, -1. And so again, like I said, this technically is an open circle here because we can't equal the coordinate point -1, 3. We don't plug in -1 to this. So the only downside of using Desmos is that this technically should like be an open hole here, whereas this one is a closed dot. So that's really the only thing that you have to be careful of with Desmos. So technically this function, this function still passes the vertical line test because you can still draw a vertical line through here and it only hits the function once. It's only going to hit the function here where y is 6 and not hit here. So this is still a function. It's called a piecewise function, and that is how you graph it on Desmos. When we plugged in certain points, we plugged in the point 2 and we got out 6. So we have the coordinate point 2 comma 6 right here. When we plugged in -1, we also got 6. That's this coordinate point. And we also plugged in -3 and we got 8. So those are just coordinate points. Again, when you plug in an x value into your function, your output is the corresponding y. If we wanted to look at this more from a calculus perspective, we could involve limits. Now, the only point where we really have to check the left and right-sided limit is at our breaking point, or our change point, which is at -1. And that's because we have the potential for the left and right-sided limits to not be the same, since that's where we change functions. If we were to, find the limit, let's say as x approaches 2, the overall limit of our function f of x. Yes, this is an overall limit, and technically we do have to see when it approaches 2 from the left and the right. But let's look and see, when we plug in 2, we had the point 2, 6, which was right here. This is where x is 2. I know we can't see it, but as we're approaching where x is 2 from both the left and the right, we can clearly see that because it's the same function, there's no breaking point when x is 2, the limit from the left and the right is in fact the same. Therefore, we don't even have to check the left and the right because it's the same function there. We know that we're not doing any moving when x is 2. It's this same smooth parabola, this quadratic function. So the limit as x approaches 2, all we need to do is direct substitution in for when x should be 2. And when we plug it in, 2 squared plus 2, 4 plus 2 is 6. We can see that the coordinate point 2, 6 is here, and that happens to end up being the limit as well as 6. However, if we were to look at the point of interest, which is when x is -1, so if we replace this at -1, we really do need to check both sides, and that's because -1 is a more important point than when x is 2. -1 is our change or breaking point. And so in order to find the limit, the overall limit, as x goes to -1, we do need to be super sure that we check both sides because, again, that's our breaking point. So the limit as x approaches -1 from the left, so we definitely need to check the limit as x approaches -1 from the left of our function. And we can do this visually, right? If we look as x, here's where x is -1, all along this vertical line. As we approach from the left, it's 6. And we can do that algebraically too. This is approaching -1 from the left, less than. So if we plug in -1 here, we'll get 6. So we can do it both graphically and algebraically. So that is 6 from the left. Then we can check our limit as x approaches -1 from the right. And since that is technically an open circle, right, I said Desmos doesn't do that well. It doesn't really matter that it's an open circle because, again, a limit is the y value that we're approaching, not the y value that we equal. So as we approach -1 from the left, our y value is approaching 3. That is supposed to be a horizontal line, approaching 3. And then we can also check that algebraically, right? If we were to plug in, where x is approaching -1 from the right. Now, this is kind of weird. You're saying, well, why do we plug -1 into this one? It's not when x is -1. No, you're right. It's not when x is -1. We want to know as x approaches -1 from the right, and this would be the function where we would direct substitute it into from the right, because greater than -1 means from the right. So if we plug in -1 into this function approaching from the right, we'll have -1 squared, which is 1 plus 2. So again, we get 3 both graphically and algebraically. So we can see that although our left and right-sided limits do exist, our overall limit does not exist because they're not equal. You can clearly see that on the graph, like our left and right sides are from -1 are not approaching the same value. There's a huge jump here in our graph. So we needed to check both the left and right-sided limits at this important change or break value of x when x is -1, because that is the most important x value in this entire piecewise function. Any other x value that we plug in, you don't need to check the left and the right-sided limits because we can see that they're a smooth curve, continuous all the way through, no holes, gaps, jumps, or anything potentially crazy on both sides of -1. -1 is the only time where we need to check because potentially there's a break in the graph and it's different from both sides. So if you're asked to find any other limit as x approaches any other number but -1, you can just direct substitute into the proper equation and you can see why visually. However, if you're asked to find the limit as x approaches the change or breaking point of your piecewise function, then you do need to double check that the left and right-sided limits are in fact the same in order to find the overall limit. In this case, they're not, so we say the overall limit as x goes to -1 does not exist. Okay, here's the last part of our video. This is the you try section. Go ahead and pause the video now in order to see how you're doing and hit play to check your work. Okay, here are our answers. These first three are basic plugging in. This is a pre-calculus method. When I say pre-calculus, I just mean before calculus. So all we're doing is evaluating at 3, so we plug in down here. 3 minus 4 is -1. The absolute value would be 1 plus 1, where we get 2. Plugging in 0, we'll plug into the top function, so -1. Plugging in 4, we plug into the bottom function, so we'll get 0 plus 1. Then these next two are calculus perspectives, since they deal with limits, the first main idea of calculus. And the limit as x approaches 5, we only need a direct substitute down here because 5 is not a change or breaking point in our graph. And an absolute value function is just a smooth v, so there's no holes or gaps in it. So as x goes to 5, we direct substitute down here, and when we do that, we'll get 2. Then the limit as x goes to 3, we do need to check both sides because 3 is our break or change point in our piecewise, and there is a chance that both pieces do not come together at the same point. So we check as x approaches 3 from the left. So we plug in up here, since this is approaching 3 from the left, and we'll get 3 minus 1, which is 2. We check the limit as x goes to 3 from the right, so we plug down here, since this is approaching greater than 3 from the right. When we plug that in, we also get 2. And therefore, since both our left and right-sided limits match, we do have an overall limit this time of 2. If you'd like to graph this on Desmos and get some practice, that's a great idea. And you can see that our two pieces do come together at the coordinate point 3, 2. All right, I hope that you have a better understanding of piecewise functions overall after watching this video. So your assignment should not be as bad this time around. Good luck.